Ever wondered why an apple falls to the ground instead of floating away? This seemingly simple question stumped some of the greatest minds in history. You see, there's an invisible hand at work here, a phenomenon we call gravity. Gravity, as Sir Isaac Newton proposed, is a force of attraction that pulls objects towards each other. The more massive the objects, the stronger the gravitational pull. Think of it like a cosmic tug of war, where the Earth always wins, pulling everything from apples to us, towards its center. Newton's theory served us well for centuries, explaining why planets orbit the sun and why we don't float off into space. But as with all things in science, theories evolve. Theories are challenged, theories are improved, and so we arrive at a pivotal question. But what if I told you that what we perceive as gravity is not a force at all? Enter Albert Einstein and a whole new perspective on gravity. In the early 20th century, this enigmatic physicist introduced a radical concept that would forever change our understanding of the universe. This was Einstein's theory of relativity, a groundbreaking idea built on two fundamental postulates. The first postulate states that the laws of physics are the same for all observers, regardless of their state of motion or rest. This means that whether you're standing still on Earth or hurtling through space at incredible speeds, the same physical laws apply. It's a universal constant, a solid foundation upon which the rest of the theory stands. The second postulate goes a step further. It asserts that the speed of light is the same for all observers, no matter how fast they're moving relative to the light source. This might sound a bit counterintuitive. After all, if you're running towards a beam of light, wouldn't it seem to be moving faster? But no, according to Einstein, the speed of light remains constant, an unwavering 186,000 miles per second. These two postulates, as simple as they may seem, led Einstein to a drastically different understanding of gravity. He suggested that gravity isn't a force that pulls objects towards each other, as Newton had proposed centuries earlier. Instead, he saw gravity as a consequence of the curvature of space and time. Imagine a trampoline with a heavy ball in the middle. The weight of the ball warps the surface of the trampoline, creating a dip. Now, if you were to roll a smaller ball onto the trampoline, it would naturally move towards the heavier ball. Not because it's being pulled, but because the surface it's moving on is curved. In the same way, Einstein proposed that massive objects like the Earth or the Sun warp the fabric of space and time around them. This warping causes nearby objects to move in a curved path, which we perceive as gravity. Gravity, according to Einstein, is not a force, but a warping of space and time. Imagine a flat sheet of rubber. This is the fabric of space-time. Let's dive into this a bit further. Picture this rubber sheet as a four-dimensional fabric, extending in all directions, up, down, left, right, and even through time itself. This fabric isn't just empty space, it's a dynamic, flexible medium that is bent and warped by mass and energy. Consider a heavy ball placed on our rubber sheet. It sinks down, distorting the fabric around it. This is exactly what happens in the universe. Planets, stars, galaxies, they all create dips and curves in the space-time fabric. The more massive the object, the deeper the curve. This warping of space-time is what we perceive as gravity. It's not a force pulling objects towards each other, but rather objects moving along the curves created in the space-time fabric. Now, onto time dilation, another mind-bending consequence of this warping. As you move closer to a massive object, time itself begins to slow down relative to someone farther away. This isn't just theoretical, it's been proven with precise atomic clocks on airplanes and satellites. Clocks flown at high altitudes where the gravity is slightly weaker and hence the warping of space-time is less, run faster than those left on Earth. It's a tiny effect under the influence of Earth's gravity, but near massive objects like black holes, it could mean the difference between hours and years. This is what Einstein meant when he said that gravity is the curvature of space-time. The ticking rate of a clock, the rhythm of time, is affected by how space-time is curved around it. It's a beautifully elegant and profoundly strange concept, but it's the reality of the universe we live in. So when we talk about gravity, we're really talking about the shape of space-time. We're talking about the dance of planets along curved paths, the slowing of time near massive objects, and the intricate ballet of the cosmos itself. So, did Einstein prove Newton wrong? Now that's a question that's been buzzing in the minds of many for years. Well, to put it simply, not quite. Let's dive a bit deeper into this fascinating debate. Newton, in his day, came up with the universal law of gravitation, a force that pulls two objects together. It was revolutionary, and it worked remarkably well for the world he knew. It explained why apples fell from trees and why the moon orbited the Earth. Newton's theory, in essence, still holds up for most everyday purposes and is used extensively in engineering applications even today. Enter stage, Albert Einstein. With his theory of relativity, Einstein didn't so much disprove Newton as he did expand upon his work. He introduced the concept of spacetime, a four-dimensional fabric where the presence of mass and energy warp this fabric, creating what we perceive as gravity. It's like a trampoline with a heavy ball in the middle. The ball creates a dip, a curve, and that's essentially what mass does to spacetime. This theory gave us a more complete and accurate description of gravity, especially for massive objects moving at high speeds or in strong gravitational fields where Newton's theory falls short. It explained the precession of Mercury's orbit and the bending of starlight around the sun, phenomena that Newton's theory couldn't quite account for. But here's the thing. Newton wasn't entirely wrong. His theory still works perfectly well for most practical applications on Earth and even in space. It's simpler, easier to use, and for all intents and purposes, accurate enough. Einstein, on the other hand, gave us a more profound understanding. He painted a picture of gravity that is more complex, more beautiful, and ultimately, more accurate. He showed us that our universe is not as straightforward as we might like to think, but rather a dynamic, ever-changing tapestry of space-time woven together by mass and energy. So Newton wasn't exactly wrong, but Einstein gave us a deeper understanding. So what does all this mean for our understanding of gravity? We've embarked on a journey today that has taken us from the apple falling on Newton's head to the bending of space-time by massive objects. The story of gravity, as we've seen, is a tale of shifting perspectives and revolutionary ideas. In the realm of Newton, gravity was a force, an invisible hand that pulled apples down and kept planets in their orbits. This understanding served us well for centuries, allowing us to calculate the motions of celestial bodies with great precision. But then came Einstein with his theory of relativity, and turned our understanding of gravity on its head. No longer was gravity merely a force, but rather the curvature of space-time itself. Massive objects like the Earth or the Sun distort the fabric of space-time, creating what we perceive as gravity. This new perspective allowed us to understand phenomena that Newton's theory couldn't explain. For instance, the slight deviation in Mercury's orbit, or the way light bends as it passes near a massive object. Einstein's theory of gravity, though more complex, painted a more accurate picture of our universe. And let's not forget about time dilation, that mind-bending prediction of Einstein's theory. The idea that time can slow down in a gravitational field is truly a testament to the strange and wonderful nature of our universe. So where does this leave us? As we stand on the shoulders of Newton and Einstein, we see a universe that is far more complex and beautiful than we could have imagined. We see a universe where space and time are woven together into a cosmic tapestry, distorted by the mass and energy within it. Our understanding of gravity has evolved, and with it, our understanding of the universe. As we continue to explore and learn, who knows what new insights await us? What we do know is this: gravity isn't just a force pulling us down, it's a key to understanding the very nature of the universe.